My name is Alan. I'm a PhD candidate at the National University of Singapore, advised by Professor Trevor Carlson. Here I present our recent work LoopPoint, which is done in collaboration with Harish Patil and Wim Herman from Intel Corporation. Processor complexity increases every year. The cycle-accurate simulation of complex applications running on large multi-core systems is essential in designing post-Dennard processors. Unfortunately, microarchitecture simulations can take an extremely long time. The graph shows that the standard benchmarks with realistic inputs can take months or years to simulate on cycle-accurate simulators. Sampling is one key solution to making these extremely long simulation times tractable. However, prior sampling methodologies are helpful only in a few cases. What we need is a sampling methodology that can bring down the overall simulation time to a reasonable duration. To this end, we propose LoopPoint, which can reduce the overall simulation time to a few hours. There are several challenges to devising a sampling technique for multi-threaded applications. We cannot use instruction count as a proxy of execution for multi-threaded applications primarily due to the presence of spin loops, which do not represent the actual amount of work done. The threads progress differently due to various reasons that are dependent on the underlying hardware. Another challenge is to represent the amount of parallelism that exists among the threads. We also need to differentiate synchronization from real work done by the threads. To solve these problems, we need to identify a unit of work that is more generic. We consider the number of loop iterations as the unit of work, which will remain the same for multiple executions of an application. The high-level design of the proposed methodology is discussed here. Primarily, we are going to answer two questions here. One is where to simulate in an application. We also need to understand how to simulate the identified parts of the application. We will answer the first question considering the repeating nature of applications. We have a multi-threaded application with inputs to evaluate its performance. We first slice the application into different chunks. To accomplish that, we perform loop-based profiling to identify loops and to generate global basic block vectors or BBVs of the application. The BBVs are clustered using standard clustering techniques. We choose a representative BBV from each cluster that can be used to generate representative regions or loop points. Now we can see how to simulate these representative regions. For checkpoint-based simulation, the identified loop points can be converted to checkpoints using the original application and the clustering data. Region checkpoints are generated, and we can start the detailed simulation of these checkpoints with sufficient warm-up. For binary-based simulation, we can use the application binary directly to simulate using the LoopPoint specification. The whole application performance can be extrapolated from the performance of the representative regions. We show each of these steps in detail in the next slides. At this point, we have the multi-threaded application and the corresponding inputs. Let's go deeper into loop-based profiling. We first record the execution path of the application to be reused for checkpoint generation. The next step is to generate a dynamic control flow graph or DCFG of the application run. We make use of DCFG to identify loops within the application. We use the application execution recording along with DCFG to identify slices within the application to generate BBVs. We introduce two important features in this stage: flow control and synchronization filtering. Per-thread basic block vectors are generated in this stage. The per-thread BBVs for each region are concatenated together to be taken for clustering. Let's discuss the central part of the profiling technique. Flow control is a feature that works as the application progresses during the profiling. It is essential to have the profiling results free from any perturbations caused by the load imbalance of the underlying hardware. To achieve this, we make sure that all threads make equal forward progress at any given time. We control the progress of the threads external regular intervals. During slice generation, we slice the application into different regions. The diagram shows an application execution at a per-thread level. The blocks represent loops that are executed at that particular interval. All regions start and end at a loop entry or exit. Assume the aggregate instruction count from all threads reaches the threshold number of instructions from the start of the region. We cannot end the region here, but instead need to wait till the end of loop A to define the boundaries using the corresponding program counters and their counts that enables us to simulate an equal amount of work every time. Synchronization filtering is another feature of LoopPoint. We need to separate real work from synchronization, as the profiling data should contain only real work. In the diagram, we have shown main as the application code and sync as a synchronization library code. When the profiler detects that the encountered block is from the synchronization library, It just ignores the profile data of that block. We represent the parallelism among the threads by concatenating all per thread BBVs to a larger global BBV. We have the execution fingerprint of each thread. Consider two threads of an application that execute the same code. In order to concatenate vectors, we first rename the basic blocks of thread 1 to be different from thread 0 and modify the execution fingerprints of thread 1. Then generate global basic block vector by adding the execution fingerprint of thread 0 and then append with the execution fingerprint of thread 1. From the previous stage, we have a set of global BBVs representing the execution of the whole application. We identify similar BBVs and cluster them using k-means clustering. The vector which is the closest to the centroid of each cluster is taken as the representative of the cluster. The identified representative regions are simulated in parallel using a simulator like Sniper. The whole application performance can be extrapolated by taking the weighted average performance of the representative regions. The multiplier of a representative region is determined by the number of regions that belong to that cluster. Let's see the results for LoopPoint. We use SpecCPU 2017 benchmarks using 8 threads to evaluate the accuracy of LoopPoint to predict runtime. For active applications, the maximum error that we get is 7.8%. For the passive case, we achieve similar accuracies. We get an average absolute error of 2.3% overall. A comparison of theoretical versus actual speedups achieved for LoopPoint is shown here. The serial speedups are limited by the total number of representative regions identified for the particular application. Now we can see the parallel speedup achieved for LoopPoint. The maximum speedup achieved is close to 800 times. You can also observe that the theoretical and actual speedups match in most cases. That is the end of the talk. We will be presenting the tools that we developed for this project at the tutorial sessions of ISCA in New York City and ISPAS in Singapore this year. Thank you for your attention.